So today is a continuation of the three-part series where I talk about training APIs. On Monday, we chatted about high-level training frameworks and how they can be difficult to work with. Today, we're going to talk about low-level frameworks and why, in my opinion, it's the best interface you can use to learn. First, though, what is a low-level framework? Well, first, let's start with what it's not. It's not the Transformers trainer. It's not axolotl. It's not TRL, and it's not FastAI, right? These are frameworks that try and wrap around what you want to do and give you one-line solutions. That is not what a low-level framework does. At the lowest level, a low-level framework is just the bare bones. Right? So nothing gets wrapped. It is purely what is going on. So this would be like PyTorch. Low-level APIs then wrap around purely that minimal version with the smallest amount of capabilities possible. So we're not abstracting a training loop. We're abstracting things around a training loop that people typically tend to do. We're not creating single command line solutions that magically go spin up training or inference providers. We're making device agnostic ways to do inference, but with keeping everything in PyTorch as much as we can. Because I work on Accelerate and it is a low-level API, all of my examples today are going to come from Accelerate. So bear with me if you've never seen the framework before. Just understand that it is a library which wraps a little bit around PyTorch to do a particular task. So in regular PyTorch, this is an example from Tom, actually. It's his gist on doing gradient accumulation in PyTorch. And this is not wrapped, nothing fancy is happening here, right? You iterate over some data, get the predictions from the model, call a loss function. In gradient accumulation, you divide by the number of steps you're accumulating by, so how many steps you're going over and accumulating the gradients before we finally update the weights of the model. We call backwards, and then if we've done enough of those accumulation steps, then we set the optimizer properly, and then also there's some conditional logic of after a certain amount of gradient accumulation steps, we evaluate the model on a validation set. Fairly straightforward PyTorch training. Meanwhile, this is the Accelerate equivalent. You create an accelerator object with a certain number of gradient accumulation steps. You call accelerator.prepare, passing in a model, the optimizer, and the training set. In this case, typically it's a data loader. The training loop looks the same. Right? This is 10 lines of code. This is like 7. We iterate through the training data set. We get predictions. We get a loss. We can call loss.backward. Technically, you call accelerator.backward, but then you do optimizer.step, optimizer.zeroGrad, and then you evaluate the model. Now, what you notice here is I don't have anything about gradient accumulation steps aside from at the accelerator. That's by design. Accelerate, as a low-level API, strictly tries to help you come up with a solution to having your code work across any backend. Now, we could have said using a trainer, and that trainer goes and handles everything, but that's not what we wanted. If there is any complex code that happens between either using a different provider, so that's like Apple versus NVIDIA versus AMD, or when it comes to going from single GPU to multi-GPU, Accelerate will handle this logic for you. So your PyTorch script is basically what you wrote with us making sure that it can scale, right? With gradient accumulation, Accelerate will make sure that the loss is properly reduced. And on top of that, a sneaky thing that happens here is when you're doing distributed training, you rely on communications, right? All the GPUs need to talk to each other at some point during the training. And during grading accumulation, we don't really need that to happen, right? Because we're not updating the weights relative to the entire cluster. We're only updating them at this point. And so if you're not careful and you just did this normally, scaled for distributed data parallelism, and went, you would have excess communications that can lead to at least a 2 to 4 times slowdown in your training code. Accelerate made sure that we enabled the right stuff so that excess communications don't happen out of the box, and make sure that your code works how it's needed with a level of trust that we're going to make sure to help you get your job done. But again, in doing so, where you bring 99% of the code that you have and we'll replace 1% of it with what we're doing. So you still have the creative control, while we just make sure that the stuff that you don't want to break doesn't break. So what does that mean then as what a low-level API does? You stay as much as possible in your raw training framework. This also means that error traces generally stay as raw as possible. So you're not digging through 1,000 stack traces because there's some magic when it involves using, say, FastAI or the trainer or axolotl, where because the model had an error, you got to go dig through 13,000 stack traces, right? We talked about this on Monday. Instead, it's 2 or 3 traces where it pinpoints to your code as to what's going wrong, not someone else's. On top of that, what low-level APIs enable is a smooth interface towards accomplishing your overall idea, right? You stay in control. And on top of that, teaching what is happening in the framework in a controlled manner. The trainer is 1,000 lines of code for you to go dig into. The accelerator class, I believe, is a few hundred. And especially with the parts that matter, which is typically at the beginning of the file, maybe 100, 200 lines of code. And so the idea is reducing friction by using tools designed for more advanced level students, but I don't think of them as advanced. I think of them more as you did the out-of-the-box stuff, the out-of-the-box stuff worked, and you want a guided way towards learning how all of this works. Right? For example, if you figure out how Accelerate works, you know how the trainer works because it's what's being used internally. And then that combines, right? As you learn the trainer, you learn TRL, and then you learn axolotl because you understand how it's happening at the lowest level. Now, yes, I have an extremely strong bias for Accelerate. Is that because maybe I've worked on it for the last 3 years? Maybe. Slight maybe. But also, it's as someone that came from a framework that was entirely magical, right? I used FastAI as my introduction to machine learning, approaching a framework that is purely based on the notion of rejecting magical things and rejecting the idea of having magical handholds and over abstraction to solve particular problems, and instead focus on a framework where, as a ground rule, we're not allowed magic. If we introduce something magical, we need to have an established trace to get there. If we go back to the Accelerate example, there's a gradient accumulation API that I don't show here. The last part is there's a with accelerator.accumulate that wraps over all this stuff. And if you go dig into it, it's a weird fancy context manager, right? It's 2 layers deep because when I was building it, Sylvain Guger looked at my code, looked at this magical context manager I wanted to write, and went, no, this is too magical. Users will get confused. It takes more than 5 minutes for me to understand how this code works. And so I had to write 2 layers deep that barely wrapped around what Torch Distributed would do whenever you're doing gradient accumulation to avoid those communications, and then built a layer on top of it. That way, if anyone wants to know what's happening with gradient accumulation, they go to the accumulate function, see that it calls one thing, and then you go look at what that one thing is, and it all makes sense, right? You're not sitting there going, okay, well, this called this called this called this, and now I have to follow all of these and understand 16 different files to understand how this framework works. Accelerate is explicitly not that. Although Stas Beckman kind of says it better. So Stas was a prominent figure for Hugging Face and helped work on the trainer. And for the last 2 years, I want to say, he has been a critical member of the DeepSpeed team and now is a part of Snowflake, which now handles DeepSpeed. So they're one and the same in my head. But we had released pipeline parallelism as a wrapper that Accelerate could do for you. And Stas took this moment to give us insight into how he uses it. Because remember, he works on DeepSpeed. He could just use DeepSpeed as a whole and use, however high of a wrapper he wants or low. And instead, the best part about it is it doesn't lock you into some training like some training frameworks do. And you bring your own training loop and use these building blocks, essentially, right? The accelerator is a building block that enables you to do many, many things, but all of them are optional. And that's by design. These high-level frameworks try and solve a lot of problems. And when they do so, they end up sort of locking themselves into situations where they can't change one thing because 16,000 other files rely on it. At a low-level API, especially with how Accelerate's built, we can add things to the accelerator as long as they're handy. But because it's not a training loop, because it's not going to affect anything else, it's an optional enhancement that we found users might like. So for instance, if we went back to the gradient accumulation problem here, let's say you wanted to do gradient accumulation yourself and you didn't want Accelerate to do this because you worry about something. Cool, then don't pass gradient accumulation steps and don't use accumulate and do it yourself. If this was the trainer, there's no way you'd have that control because you would be relying on their implementation of gradient accumulation. In Stas's example, he has a training loop that he's built where he tries to compare and contrast the performance of PyTorch's FSDP and DeepSpeed 0. And with Accelerate, he just has to call a single flag whenever he's launching the script, and it will do that switch for him. And he can keep track of how well things are going, how he needs to change, how DeepSpeed is performing, and whatnot. But the idea is to enable this stuff for even senior developers, right? Stas is a brilliant mind who has trained more models and built more frameworks than I have experience with. But he still uses Accelerate because it does just enough to where he can do what he needs to do and do the insane hacking that he does into training frameworks, and especially in his training loop, but make sure that the stuff that doesn't matter to him gets done in a way that he trusts, in a way that's readable, and in a way that, most importantly, is trusted in the community. Now, what does that mean? That means you take a low-level framework, you learn what you need to, and then you go back up. If I could make a chart of where one axis is, this will be time, and this would be like API level. So we're going to start up high, and then now we're down here where we're experiencing learning the low-level framework of it. And then typically, you'll go to a high level and then stay there. Well, that doesn't make any sense. You just talked for an hour on Monday about why this is bad and why this is good. Why is this better? Well, the answer, my friends, is because you learn what you need. At the lowest level, right, Accelerate is a teaching vector. So what did we learn? We learned what distributed training is without needing to actually program it ourselves, right? You didn't need to sit there and go dig through the DeepSpeed code and understand how DeepSpeed works. You have a minimal API that does a minimal amount of wrapping to basically use this framework. Accelerate makes sure that the errors you're getting are user errors, right? This will be things like NCCL timeout issues, CUDA errors that come with the loss function, and other alignment problems. And you don't have to worry about does this come from the training framework or does this come from my code? And on top of that, if it does come from the training framework, how do I identify where that timeout is? With Accelerate, it's in a very few specific places where it would get caught in a situation like this. More likely than not, though, it stems from your code because the communications happen explicitly inside Accelerate. So now you're not chasing down errors, because if you've ever had to experience debugging NCCL issues, they're not fun. You can waste many, many hours trying to figure out where they come from using high-level frameworks without actually solving your problem. And most of all, the idea with at a low level is you get that first win, right? You ripped out all the code that you were wrapping around. You went to the lowest level possible. It still worked, and you understand what's going on. And now it feels a bit more rewarding because you didn't just tell Axolotl, go train. Instead, you were in the weeds. You understood what your code did. You built it yourself. And sure, it did some magical nonsense to get it working on like multi-GPU, but you were still involved for the entire process. So why does that matter, right? Why does making sure that you're involved in the process important? Because when you're involved, especially heavily in your own training, by doing so, my personal path has found that it leads to passion. By removing the helpers, you're tackling the root problems. And you discover which parts of certain frameworks and certain ideologies you like the most. Slowly, you accept more and more help in particular places through frameworks because you've identified that, say, there's 24 things that I do. Of them, I only care about 6. So low-level frameworks help you do the other 18. And that way, those 6 are what you focus on and you learn. And then, whenever you want to go learn those, you can. Or to be placed a different way, you begin a journey of a T diagram. Now, if you've never heard of the T diagram, it is a lecture given, I believe it by a Stanford professor, that describes learning a subject. And typically, the students at Excel start by learning breadth, right? So if this is the art of distributed learning, or let's not even call it distributed learning, let's call it machine learning. Over here, we might have vision. Over here, we might have tabular. And over here, we might have text. And then we might have inference. And you have all of this knowledge that comes from the variety of topics that you can get in this landscape. And then you find the one you're passionate about. For me in college, this was tabular. So you get really invested in tabular. And this is now your T. You have the breadth of understanding the problems overall, and you have the depth in one particular area. Now, does that mean that you become an expert in tabular in every sense of the word? No, actually. Instead, what you do is you use this T diagram, right? You use this depth to facilitate the learning of the other things that are needed, right? So if we think about inference, I care about inference when I do tabular. I care about interpretability when I do tabular. I care about model performance, which will mean that along the way I wind up learning things like Torch compile. And so you use this learning vector as a way to build your expertise. And it doesn't matter what that's applied on, right? This could be the same with frameworks where, we have Axolotl, we have the trainer, we have TRL, and we have Accelerate. And this is you exploring Accelerate to its largest extent, or the trainer. And then when you've built enough experience in this domain and you start bridging into other places, you have a new T because you now understand inference and all these other subjects in this capacity, leading to another breadth. And then you specialize, very good, Mert, in a new area under all of this. And you slowly can learn and build more and more skills by doing this. If you have not structured your learning in the form of a T diagram like you're doing here, I would highly recommend doing so, because it is what is the difference between someone that's decent and likes what they do and someone that naturally builds their passion to want to learn everything. Because there's no rubric as to what you specialize in, right? Sure, we've got flashy and poppy things nowadays that talk about how you should be learning, right? The things you should be learning, like you should be learning inference, you should be learning VLLM, you should be learning Llama CPP, because this is what everyone's serving on. This is all the noise, right? This is all the breadth. You should be aware of them. You should be aware of the tools, but just pick one. Pick one tool and use it extensively. Use it to the point where you're causing problems and headaches for the developers because you're trying to push it further than what it can do. Now you have your depth. You can go take those lessons, revisit it back to the other providers, and it makes a lot more sense suddenly. The problems that you face in one framework, you'll face in another and another, because they're all built around the same foundations. The foundations, low-level APIs, it's all connected, right? The longer you can stay at exploring an avenue for as deep as that problem can go, be it low-level APIs or what have you, the stronger you become as an engineer, because there's no shortcuts into getting this experience. It is simply sitting there with the code every single day and just experimenting, tinkering, right? Because you found a topic that you're interested in, and naturally you have curiosity with it. And so you go explore it to the ultimate depth you can as a learning vector to understanding the problem at large. And really, did I intend for this to be a lecture on how to find your passion? No, but most of my rants tend to get there anyways. So hey, here we are. The idea of low-level frameworks, on one hand, is to help you understand what your errors mean, right? Because it doesn't make sense to sit there and debug a high-level framework where you don't know what's going on, you don't know what the magic is, and you're trusting it'll work, and then magically you have a project due in 2 days, and you're relying on the developers to fix a problem. Don't handicap yourself like that. Do the effort at the start to dig deep and take those training wheels off and learn as much as you can about what's going on under the hood. That way, as you go learn a new skill or you go apply a new tool, you can see it through a different light. And it makes a lot more sense now. The errors are more sensical. You're not as frustrated digging through the code because you're prepared for what the code should be saying, right? You're no longer hitting an error with transformers where it talks about matmul issues. You immediately know a matmul issue is a modeling error, the 3 different ways that can happen. And now you know what to go look at in the trainer to go see where that code lies. You built yourself a roadmap to help you debug the problems that you're experiencing every day. That way, whenever you do go and you do want to get it done, you understand what's happening. So thank you so much for letting me rant for a while. I will take questions at this time. Mert has a comment of top-down is awesome when it comes to prototyping, but bottom-up helps you develop systems that have complex features and value proposition. Exactly. I fully agree with that. Top-down is exceedingly important because top-down gets you the spark, right? It gets your foot in the door. And then eventually, you're going to need to figure out what your bottom-up looks like in order to make sure that you're not just a tool user, you're an expert matter in what the tool is doing. The example I will bring up over and over and over again, because it is what I got my start on, is FastAI version 3. This was 2018 and 2019 editions of the course. In the first lesson for FastAI, you identified cats and dogs. By the 3rd lesson, you were dealing with tabular data. By the 5th lesson, you were building apps for doing like language models. Right? This was ULM Fit. This was almost 6 years ago. And The idea was you took the first lesson, it got you hooked, you could go spark your imagination because FastAI lets you do these magical things. Then the part 2 came out, deep learning from the foundations, where immediately you're now building PyTorch from scratch. And so you're building this bottom-up approach, but under the context of everything you had in the prior course, right? So you could take this bottom-up approach and go with the end goal of, okay, well, eventually I want to make this work as an image classifier and repeat what I did for lesson 1 by identifying cats and dogs. Use that learning vector to help you understand everything else that happened in between. And those 2 courses combined, but even realistically, just taking the second course and having a passion and idea in mind, is one of the strongest classes out there when it comes to understanding the tools we use today, how they're built, why they're built, and making sure that you can use them as effectively as possible. Everyone's writing solutions to the same problem. What's different is their opinions on how it should have been built. Okay, so we have a question of what other frameworks like Accelerate are the ones you'd categorize as a low level? So this would be things like Nanotron, Accelerate. I believe there's like Megatron Small or something like that. Torch Titan is another one, where essentially it's low-level frameworks are ideas where even if they wrap, per se, a lot of code, like Torch Titan does, the key is making sure that when you visit the code that's working under the hood, does everything that relates to your problem and what you're doing can fit roughly in one file. And as you deal with more complicated APIs, they're not going to be the most simple things in the world, right? For instance, Torch Titan is a pretty complex framework that looks very simple at the start. But it's simple solutions with very low-level implementations. So you can still study them and you're not digging back and forth between things. It's a very high reading level because of what they need to do. And as Pavel said, no one's going to write easily a package like Megatron Core from scratch. No, but you could write a small training framework from scratch that wraps around essentially what Accelerate did, right? You could recreate Accelerate from scratch. That's what Jeremy's part 2 did. You create a PyTorch training framework, a low-level FastAI, from scratch. In doing so, you can tailor things to make it easier for you to integrate with certain problems and certain solutions that exist that maybe the frameworks you're used to using had a hard time with it. They didn't want to implement the feature, but you still wanted to do it. And that was a blocker. Also, what do you think of using PyTorch directly? And what about things like JAX? I have no comment on JAX. I've never played with JAX. I know scientists love JAX. But for me, I started with PyTorch. I will probably end only doing PyTorch because I enjoy it. The comment about what about using PyTorch directly? You can. No one's stopping you. The idea of staying at a low-level API is to facilitate the learning of behaviors that PyTorch does, right? So if you studied Accelerate source code, you learn how we deal with distributed data parallelism, how we deal with deep speed in a way that's applied, targeted, and not just following an MNIST tutorial, right? You're following, say, like the NLP example Accelerate has. You ran it in Accelerate, you understand how it works, or you take a trainer script, and then you peel back the layers and even peel back Accelerate and re-implement what Accelerate did for one particular problem. This is actually the most common use of Accelerate, is they get the training script working, it works on multi-GPU, eventually they settle on a particular solution, and so they rip out Accelerate, right? They go learn what Accelerate is doing in all of its capacities, and they decide that 0.2 is the distributed training that they want to do and they will stick with. So they rip out Accelerate and go learn how to do 0.2 and put it in there. Does my heart break because they're not using Accelerate? No. Accelerate's being used in the trainer. We already have usage metrics, everything's fine. What I love about that is it helped you learn how to do this on your own. And so those same people are the ones that will go through and help on Accelerate issues. they'll go write educational content on how this stuff works, right? Because if I can write a framework where you can then go write your own framework that's like the framework I just made, taking all the lessons from it, all the ideas, all the tools, and the lessons from it, and do it yourself, then I know that you have accomplished a deeper understanding of how frameworks work, and especially how distributed training works. Now, yeah, you're not going to go implement Megatron Core. That's insane. That's a very high bar. If you do, more power to you. You should have a high-paying job somewhere. That's not the goal. The goal is to get something rudimentary that works, that you can tailor towards your needs to help solve your solutions at the high level eventually. So to the second part of your question of what level do you start at, it's sort of the, I gave a really good talk about this yesterday as part of Hugo's course. The level you start at is the level you're most comfortable with. And then go one level lower, right? Start your learning there. Don't say, I'm going to go from the Hugging Face trainer to pure PyTorch. You'll probably get frustrated. You'll probably hit a lot of issues and you'll probably be confused. That's not the journey we want, right? It's not something to where it should be frictionful to an extent of you want to quit, right? You should be able to have some sort of journey where you can hit easy wins by targeted metrics as you go along. You're recreating Accelerate from scratch. You got DDP working. You saw speed up with DDP compared to doing single GPU training, and it's on par with what Accelerate does and what PyTorch does out of the box. Great, there's your easy win. Then you build off that. A little more and a little more and a little more. Magically, by the end of it, you could be implementing what Megatron Core does at some point throughout that journey, because you hit the easy wins and the quick wins and the wins that get you the most value by learning what these frameworks do and the knowledge they help you understand to go explore harder problems and build these things, right? Most of these frameworks that are these magical tools that do a lot of stuff, this is just a side tangent on top of a side tangent, are typically built by one person, usually. FastAI as a whole was mostly built by Jeremy Howard, and then Sylvain Guger came in. Accelerate was nearly purely built by Sylvain. That's why I called them opinionated frameworks. And so use that and use your own opinions to rewrite a framework and tweak it to your needs, to your designs, to what you believe is the right way. If everyone else says it's the wrong way, that's fine. You're not building it for them. You're building it for you. You're not building something meant to be in production for 9 years. You're meant to use it as a learning vector. Learning is messy. Learning leads to disgusting code. And that's sort of how that goes. All right. Lath goes, I guess it helps to know the levels. So in their example, we have PTX to CUDA to Torch to Accelerate to Transformers to TRL to Axolotl. PTX, I'm assuming, just means C++ code, I imagine you're going at, because that's how sort of I think about it. So we have, so like if we think about going from the lowest level possible to the highest level possible with PyTorch, and especially with Transformers, right? So we would start at the C+ kernels that back PyTorch and do all the fancy math that Python is far too slow to do. And then you have PyTorch, which facilitates an API that lets you use those kernels. CUDA exists somewhere in here. I feel like it's more at this level. Then you have Accelerate, right, which exists as a low-level wrapper around PyTorch. And then you have the trainer. And then you would have TRL, and then Axolotl. So yes, your guess of how you would envision the stack would go is perfect. How does MLX and Apple hardware for training at low level? That's a fun topic. In my eyes, the only things that I trust numerically to train things are TPU and CUDA. That's just the state of things. I have not seen impressive enough results to where I trust MLX and other frameworks to really do training. For inference, phenomenal. Legitimately sitting here debating on if I want to buy a MacBook just so I can run Kimi K2 at home because it's so good, and the price per like gigabyte of memory is insane for MLX. But for training, it's still decently far. The things you want to care about is watching what people say about numerical stability, especially at low precisions, and throughput, right? True throughput, not fancy numbers. If you want a good rundown of what the different providers are that are good and work, Stas's ML engineering book has an entire hardware section. It's free, open sources on GitHub. Just search Stas Beckman ML engineering. And it's got a whole section on the different compute providers you can have between AMD, NVIDIA, and whatnot, and what he has personally used and found works when he's training gigantic models on gigantic clusters. So that is my advice for that. Any other questions before we sign off? Honestly, the fact that we landed at 140 is phenomenal. Yes, the third talk for Friday. I just made it a moment ago. I will be adding everyone that is present in here. If you've signed up to this talk in general or the prior talk, I'll be running the script to get all of you in there shortly after this is over. At 11 on Friday, we're going to talk about the high-level API again and why having this context at the low level helps you get there. 11 a.m. Eastern. And, if you can't make it, I will have a recording out by the following day. So thank you guys so much for joining and listening to me yap. This is obviously something I'm very passionate about because it is sort of my life's essence, my life's passion, and my life's journey. And so I'm very happy that so many of you are also interested in this because it's a very real subject for me. So it makes me very happy. Thank you all so much for joining, and I hope I see you on Friday. If not, there will be a discount code to the course coming out in a month. It's also been sort of a gigantic project of mine, so if you will at least consider showing up, I appreciate it. See you Friday.